So when we ask ourselves that, say for example, what is in our mobile phone? What we see there is that it is essentially chips, right? Consisting of resistors, transistors, capacitors, right? There are inductors, battery, of course. So electronic devices, okay? Electronic components, we say. So what we do, we put enough of these together and we can make a phone or a PC. What do we do with all these things is the key is the representation of information. In the form of zeros and ones. It is that simple. So it's these are ones and these are zeros. So that is like the information, this being 1 and this being 0. And these electronic components can work with this representation of informations. They can work with this. They can store such results. They can calculate various different mathematical formulations using just these kind of representations. And all these electronic components can actually work with this representation of information. And over the last 40-50 years, the engineers have been miniaturizing these circuits. Okay. And these circuits are getting smaller and smaller and smaller. Okay. Smaller than a human hair. Then smaller, such small that it cannot be seen with the naked eye. And engineers are making it smaller still. So in a regular classical transistor circuit, okay, there are now billions of these components, these electronic components. There are now billions of these components in the space. And how are these things made? They are developed onto silicon using techniques similar to that of photography. So what happens when we make these circuits even bigger? So these classical circuits, when we make it even bigger, they're currently made in large sheets of silicon. Okay. Unfortunately, they're reaching their limits in some way. And these silicon devices are not going to work forever if we want bigger processors. Why? Because there are two main problems. One is that the components face an overheating problem. And the second problem is a different kind of law. When I say laws of physics, a different kind of physics, I would say, that apply to such very small objects. You all guess what kind of physics is that? Yes, and it is the quantum physics. So this overheating is why this overheating is happening. It is because that this transistor have resistance and billions of teeny resistance inside each chip. So we pack more and more into a small space and the chip overheats. So you know that those computer chips need huge heat sinks, and chips are really, I mean, if you really say that chips are really two-dimensional, but they need huge heat sinks, okay? And computer needs to become more and more powerful to run bigger and bigger programs. And in managing this heat, what is happening is that we are consuming a large amount of electricity to run all these computers.
So we were talking about this miniaturization. Now this miniaturization is natural. Why do we do miniaturization? It's basically to avoid wastage. Avoid wastage. Wastage of what? Wastage of time, space, and energy. To get to the most efficient computing. All right. So we saw that the two problems that we talked about, one is overheating and another is the entering of the quantum realm. These are the two problems that we talked about is actually affecting this miniaturization. We cannot go beyond a certain limit. So what if we could use a material that does not generate these problems, And what is such a material. Such a material is a superconductor. What is a superconductor? It is a particular material that below certain temperature, it has no electrical resistance, zero electrical resistance. How does it look like? We can represent this with a graph. So here on the x-axis, if we plot the temperature T, and in this axis we plot resistance R. We see, and this is 0 Kelvin, we see normal metals that we normally use for even silicon for that matter. They have resistance, okay? And the resistance grows as the temperature increases, okay? And it is not zero at 0 Kelvin. However, for superconductor, this is something else. If the superconductor is maintained at a particular temperature, Tc, and it is called the critical temperature. Beyond this Tc, when the temperature is lower than Tc, the superconducting material has no resistance. And as the temperature increases, the resistance increases. So this is a superconductor, and this is an ordinary conductor. So since below this temperature there is no electrical resistance, very large current are possible, right? And very large currents are possible. That means no power dissipation. So we can save on energy, we can save on space, okay? And how we can save on space is because there is large currents are possible and no power dissipations. We can pack many components together. Right? Now, what are superconductors made of? The superconductors can be metals. Right? Usually we see for metals the Tc is nearly from 1 Kelvin to 10 Kelvin. It can also be ceramics. Like say for example, these metals, it can be niobium, for niobium Tc is around 9K. It can be lead. The TC is around 2K. Aluminium TC is around 1.2K. Ceramics usually have better TCs. So the critical temperature for ceramics are of the order of 50K to 130K, which makes it easier to work with ceramics, but the ceramics has more complicated structure. A commonly used ceramic is called YBCO. It is yttrium, a ceramic composite of yttrium, beryllium, copper, and its critical temperature is around 90K. Right? So how do we achieve these temperatures? What we do is we use cryogenic cooling. And two main cryogens are liquid nitrogen. Its temperature is 196 degree centigrade, which is around 77K. So you can see in this liquid nitrogen, YBCO works pretty well. YBCO achieves the superconducting capabilities. Another is liquid helium, liquid helium. It is about minus 269 degrees centigrade. It is about 4K. Now remember, in Antarctica, the recorded lowest temperature is minus 89 degrees centigrade. So imagine how cool they are. Now in university labs like say Caltech, the refrigeration equipments that these labs has, they can reach a temperature of 20 millikelvin. They do something more with this liquid helium, and it can reach about 20 millikelvin. So it is just 0.02 degrees centigrade above absolute zero. What is absolute zero? It is minus 273 Kelvin. Now what happens is in such cold temperature, the properties of many materials change. Say for example, a rubber tube, okay? Rubber tube, you know how a rubber tube looks like. It has a rubber elasticity. If you stretch at the tube, it extends and so forth. When you dip a rubber tube into a liquid nitrogen, for example, what happens is it becomes very hard. So basically this such low temperature alters the physical characteristics of materials that achieve the temperature similar to this. And for metals, if we lower the temperature, the electrical resistance of metals goes lower and lower. Now suppose we have a copper tube. Okay. And we drop a small magnet in it. This is a magnet, and this is a copper tube. And I drop a small magnet in it. What will happen? Normally, the magnet, if there is no copper tube, the magnet falls straight away. But with a copper tube, the magnet will fall slowly. Why is that? Because a moving magnet causes currents. Okay. And these flowing currents, so it will cause a current. Okay. And these flowing current will cause a secondary field. Okay. And this secondary field oppose the first current. So there is a force above and there is a force below, which is the gravitational force. And with the effect of these two forces, this magnet falls very slowly through the copper tube. Now if we cool this copper tube in liquid nitrogen, say for example, okay, what happens is the resistance of this copper tube reduces. Okay, so the current that are produced on the copper tube flows for a longer period of time. They eventually die away as they heat the metal, yeah, but they flow for a longer period of time, and hence this upward force gets even stronger and also for a longer period of time. So a copper tube cooled in a liquid nitrogen, if the magnet falls through it, it falls even more slowly. That's an interesting experiment, that how liquid nitrogen or temperatures of this sort lowers the resistance of the copper, and how that lowering of resistance affects the movement of magnet through the copper tube. Okay, but now copper is an ordinary conductor. Unfortunately, we cannot make the resistance go away completely for a normal conductor. But with a superconductor like YBCO, we can achieve zero resistance. Say suppose we take a YBCO plate. Suppose we take an YBCO plate, and this is an YBCO plate or a block, and this is cooled to liquid nitrogen, that is enough, which is about 77 K. Yeah. and this YBCO reaches the superconducting stature for 90K itself. So 77K is quite superconducting. And then we put a magnet on top of it. Okay, if we put a magnet on top of it, what will happen is that this magnet is like north south like that it will float on the YBCO plate. That is another example with the superconducting that materials that we can do. It floats on the on this YBCO block. Why? Because when the magnet comes very close to the plate, the current starts flowing in the YBCO block, and it has zero resistance, so the current do not die down. Okay, it keeps moving into the plate. So this current continue opposing the magnet forever, or at least until the YBCO plate warms up. If we leave the YBCO plate to warm up on its own, after some time the magnet drops because the superconducting current dies down. But if we maintain the temperature of the YBCO plate, it will float forever. Alright. So what are the primary applications of superconductor? As you see that they can generate very high magnetic fields. Okay, because larger current can be produced within these with no resistance. So MRI scanners right, low loss transmission of electricity, right? Levitating trains, things like that can be achieved. A very interesting application is in the medical technologies. Which is where we can use the superconductors as very sensitive detectors, of magnetic fields. Like very teeny magnetic fields. Such magnetic fields appear where? Like look at the brain scans, okay, and detect the very teeny magnetic signals. Signals in the brain. Okay. So these superconducting transistors, so we make transistors as well from the superconductors, the superconducting transistors. They will have no heating problem. So the first problem is solved. So they will be efficient, right? They will be efficient and can be stacked in 3D blocks. Right? Now remember the second problem. superconductor also solves the second problem. And what was the second problem? Working in the quantum realm. So superconductor also solves this problem because they use these different laws of physics as part of their operation. Right? And what is that? Like saying in electronic circuits, the electron waves are too small to control. Like in conventional electronic circuits, the electron waves are too small to control, but they are large enough to cause problems. What happens in superconductors is that these electron waves, get very big. So these electron waves get very big, okay, and it becomes, how big? It's big enough for us to control them. Okay. So that is the benefit that we get by implementing superconducting transistors. Now here is an interesting experiment that we need to talk about with this superconducting materials, which is basically called a SQUID device. Okay. And this SQUID stands for Superconducting Quantum Interference Device. What is it? It looks like this. It's look like such an arrangement. Okay, so this is superconductor. What happens when the electron goes in there? A loop, this kind of a loop. Okay. Made out of superconducting material. What happens is that the electrons goes either way. Either way. And if we output this to an oscillator, okay, we get to see curves like this. So these are about 200 microampere pulses, and we get to see the oscillations like this in a noise-free environment, of course. Now, what is this? This is very similar to interference fringes, okay, that we get to see in Young's double-slit experiment using standard light. What happens there? That coherent light form interference patterns. The same thing happens here. Look, the electrons in this superconductor, they behave like coherent waves. Okay. So with this experiment, we can really see, like, this is a large device, and it looks large, but it's really very teeny. But even like a macro object. Okay. So in a macro object, we see quantum mechanics happening at a large scale. Okay. So such quantum waves, like so basically electrons behaving as coherent waves. So this quantum waves has a peculiar property. What is it? It looks like a wave, feels like a wave, like that. And the waves allow, we write it down, wave allow the electron to spread out. Okay, the electrons get spread out. And as a result, they can be in two places at the same time. It feels like, but not really. Okay. So, like this and this, there is a possibility that we can find the electron here. There is a possibility that we can find an electron there. And if we term these two possibilities at two different states, say a 0 and a 1, okay, then there is a possibility that we can, once we measure, we can have the electron maybe at state 0 or a state 1 or anywhere in between. Okay. I mean, the electron is anywhere in between, but when we measure them, we will find either it is here or it is there. And this is the thing that is known as a superposition. And with these concepts, we will come into the concept of qubit. With these superconducting qubits, we get to see a benefit immediately. Suppose we have a classical resistor. We have two resistors that can take 1 bit, that can store 1 bit at a time. Okay, and with these 2 bits, we form a 2-bit number or 2-bit entity. So, suppose we want to have 0, 0. Suppose we want to get 0, 0, then 0, 1, then 1, 0, and 1, 1. How many steps we have to do this? Okay. In the first step, we have to store a 0 and a 0 in these two resistors to achieve this. In the second step, we have to put a 1 in this resistor. In the third step, we have to store a 1 here and a 0 here, these two resistors. And in the fourth step, we have to store a 1 here. So there are 4 steps required. Whereas in quantum resistor, these two resistors can simultaneously have a superposition of states. Okay. Now this superposition, we will show this later on. A superposition of state we write as psi, which is alpha 0 plus beta 1, superposition of states. And so we can achieve these states like 0 0 0 1 1 0 1 1 at the same time. So in one step we can achieve all this, and later we will show that using a particular gate we can achieve this in a single step using 2 qubits. Okay. Now not only the superconducting qubits, but there are other ways of realizing qubits, and these are also experimentally happening, which is one is ions trapped in electric field. B is nuclear spins. Like within an atom there is a nucleus, and you can use the nucleus as a storage device to store different states, different quantum states. Okay? And you can manipulate the nucleus in order to do mathematical calculations. Thirdly, we can use photons from lasers, see, and you can use these photons as qubits. So here ions as qubits, nucleus as qubits, photons as qubits. So all these experiments are happening. So essentially you will see that in later on with such superposition we can explore several calculation probabilities, calculation possibilities at the same time, and this is known as the parallel computation. And we'll elaborate these topics, all these topics, in the subsequent videos.